There was a time when reaching another world seemed like the privilege of only 2 nations, as if the heavens had room for just 2 voices. The story felt simple then. Giant rockets rose, flags were planted, and history appeared to move along a narrow line drawn between Washington and Moscow. But space was never really that small. Beyond the glare of the superpowers, other countries were watching, learning, improvising, and dreaming in quieter ways. Some arrived with modest budgets, some with fragile institutions, some with almost no expectation that the world would remember them at all. And yet, once you begin to notice them, the familiar story of space exploration starts to change shape. It becomes stranger, broader, and in many ways more human. Because the real question is not who won the space race, but who kept racing after the world stopped paying close attention. When most of us picture the space race, we imagine the Cold War at full intensity. We see the Soviet Union launching the first satellite, then the first human into orbit. We see the United States answering with the Apollo program and the first footsteps on the moon. It is an image built around spectacle, urgency, and national prestige. There is truth in that image. Those missions did reshape history. They changed science, politics, industry, and the way humanity thought about its place in the universe. But that familiar picture also does something misleading. It compresses space exploration into a duel. It makes the rest of the world seem like an audience sitting at the edge of the arena, watching 2 giants decide the future overhead. If we keep looking at history that way, we miss something essential. We miss how widely the desire to explore spread. We miss how many nations built their own ambitions out of scraps, compromises, unexpected strengths, and sometimes sheer stubbornness. We miss the fact that once the first era of lunar triumphs faded, a second, quieter race began to take shape. That newer race does not always announce itself with the same thunder. It is not always driven by the same need to humiliate a geopolitical rival in front of the entire planet. Often, it looks more subtle than that. A nation sends up an orbiter instead of a crewed capsule. Another develops a lander precise enough to touch down near a specific patch of rock. Another studies a neighbouring planet, not only to prove that it can get there, but to ask a question no one else has framed in quite the same way. Step by step, mission by mission, the map of space exploration begins to fill in with new names. And once those names enter the story, the meaning of the story changes. Space is no longer just a theatre for raw power, it becomes a mirror. In it, nations project anxieties, pride, aspiration, trauma, scientific maturity, and long-term intention. Some go to space to demonstrate capability, some go to diversify their economies, some go because prestige still matters, some go because planetary science opens a path to better understanding Earth itself, and some go simply because once a civilization becomes technically able to reach outward, it becomes very difficult to resist the pull of that possibility. Few missions capture that shift more clearly than India's first successful journey to Mars. On paper, it sounds improbable enough to be mistaken for a myth made after the fact. A country, not usually centered in Western narratives of deep space exploration, launched a mission to Mars and inserted it into orbit on the first attempt. That alone would have been remarkable. Mars has a long history of humiliating engineers. Reaching it is difficult, entering orbit around it is harder still. To do it on a first try is the sort of achievement that instantly forces everyone else to look again. What made the accomplishment even more arresting was the cost. India's Mars orbiter mission was often described in terms of how inexpensive it was compared with other interplanetary projects. There is always a danger in reducing a scientific mission to its price tag, as if frugality itself were the whole point. It was not. The point was competence. The point was that a nation working with more limited resources had demonstrated a level of systems engineering, planning and execution that no one could dismiss as symbolic. This was not a gesture towards space exploration, it was space exploration. And yet the deeper significance of the mission lies in something more than the fact that it arrived. It lies in what the mission revealed about the changing culture of planetary science. Mars had already been visited by American and European missions. Its surface had been mapped in immense detail. Its atmosphere and geology had already generated a large scientific literature. So a natural question followed. What could another mission add? The answer turned out to be unexpectedly beautiful. India's spacecraft entered a highly elliptical orbit around Mars. At its farthest point, it could see huge portions of the planet at once. At its closest, it could still approach the surface closely enough to pick out major terrain features. This orbit was different from those used by missions designed for relentless close-range mapping. It did not always stare downward at maximum detail. Instead, it often stepped back. And in stepping back, it gave Mars something close to a planetary portrait. That difference matters more than it may seem at first. Much of modern planetary science advances through specialization. One instrument measures mineralogy, another traces atmospheric escape, another maps subsurface ice, another photographs a small patch of ground at extraordinary resolution. Each is valuable. But when you step back far enough to see Mars almost as a whole world again, you recover something ancient and powerful. You recover perspective. From that wider vantage, the planet begins to look less like a collection of disconnected problems and more like a coherent place. The polar caps become visible, not as abstract data points, but as bright, fragile extremes at the ends of a weathered globe. Dust storms unfold, not as isolated local disturbances, but as continental-scale events, spreading in shapes that remind you Mars is still active, still dynamic, still capable of rearranging its own appearance in a matter of weeks. Vast shield volcanoes rise from the plains. Long chasms cut across the crust. Cloud formations gather over elevated terrain. Wind leaves its signature in patterns across the ground. What India's Mars Orbiter mission offered was not just information, but a way of seeing, and that matters in science. The questions we ask depend partly on what kind of world we believe we are looking at. A close view can reveal process. A distant view can reveal relationship. Put the two together and the planet becomes richer. Seen from orbit in true colour, Mars also becomes harder to reduce to cliché. It is not merely the red planet in the simplistic sense. It is red, yes, but also brown, gold, rust, grey, and pale where ice and cloud or dust alter the scene. The surface bears old scars, but not all scars mean the same thing. Some are impact craters, others are valleys, channels, troughs, collapsed terrain, or volcanic structures. Even from a distance, you can begin to sense that the history of Mars is layered. Water, lava, wind, impacts, freezing, sublimation, atmospheric loss, and time itself have all written on the same surface. That is one of the great themes running through the modern exploration of Mars. It is not a dead world in the ordinary sense. It is a world whose most dramatic chapters may be in the past, but whose present still contains motion. Dust devils stretch shadows across the ground. Water ice clouds gather over volcanoes. Atmospheric particles continue to leak away into space. Seasons pass, winds move sediments, frost appears and vanishes. The scale is different from Earth, and the tempo is slower in some respects, but Mars remains a planet with systems, not a fossil frozen in absolute stillness. Once you start to think of the story that way, another shift becomes possible. Missions from outside the traditional centres of space power are no longer just participating in exploration after the important discoveries have already been made. They are actively changing the kinds of questions we can ask. A mission can contribute not because it goes where no one has gone, but because it looks differently, prioritizes differently, or connects phenomena that earlier investigations treated separately. That is the beginning of a much larger transformation. The old image of space exploration suggested scarcity. Scarcity of launch capability, scarcity of knowledge, scarcity of entry points into the heavens. The newer image suggests multiplication. More launch providers, more national agencies, more instruments, more scientific cultures, more reasons to go. The universe does not become smaller under that pressure. It becomes more available to interpretation. And that has consequences beyond prestige. When more nations reach outward, more societies begin to see themselves as participants in the long project of understanding the cosmos. Children growing up in those countries are no longer told that space is where other people go. Engineers no longer have to imagine excellence only in imported form. Policymakers begin to see deep space not as a distant luxury reserved for wealthier states, but as a field in which domestic capability can be built. Even the symbolism changes. A spacecraft at Mars becomes evidence that scientific modernity is not the private inheritance of a few historic powers. This is one reason the new era of exploration feels so important, not because it replaces the old one, but because it completes it. The first space race proved that humanity could leave Earth. The second, quieter race is proving that humanity is wider than the first story allowed. Different nations bring different institutional histories, different scientific priorities, and different political meanings to the same celestial targets. Mars, the Moon, Venus, Jupiter all remain the same worlds, but they begin to acquire new significance depending on who is looking, why they went, and what they choose to notice. India's achievement at Mars is therefore not just an isolated national triumph. It is an announcement. It says that deep space exploration has entered a more distributed age. The gates did not swing open all at once. They opened gradually, through decades of technical groundwork, modest ambitions that became larger ones, and a willingness to attempt missions that outsiders sometimes underestimated. Once that pattern begins, it is hard to contain. One nation reaches Mars, another asks what it can contribute there. Another looks to the Moon, another studies Venus, another imagines Jupiter. Space ceases to be a narrow contest and becomes something closer to an expanding civilizational frontier. And Mars, perhaps more than any other planet, invites that expansion. It has always drawn human attention because it feels both familiar and estranged. There are deserts there, storms there, clouds there, canyons there, volcanoes there. It hints at a lost habitability without surrendering its full history. It seems close enough to understand and distant enough to remain mysterious. Once India had shown that another path to Mars was possible, the question was no longer whether the old powers had been joined. The question was how many more voices were about to arrive, and what they would see once they did. That question becomes even more interesting when we move from India's mission to another country, whose arrival at Mars carried an entirely different kind of symbolism. If India's orbiter showed that a first attempt could succeed through disciplined engineering and carefully chosen mission design, the United Arab Emirates' Hope mission showed that a very young space program could leap outward with astonishing boldness and still ask serious scientific questions once it arrived. In some ways, the mission seemed to skip a step. Many countries build toward deep space slowly, establishing one capability at a time, remaining close to Earth until institutional confidence catches up with ambition. The United Arab Emirates did something more daring. It chose Mars. And it chose Mars not simply as a stunt or a flag-planting exercise, but as a scientific destination whose atmosphere, seasons, and weather could be studied as an integrated system. That distinction matters. It is tempting to hear that a nation has reached Mars and to frame the achievement only in geopolitical terms. Who got there first? Who spent less? Who proved what to whom? Those questions are not meaningless, but if we stop there, we reduce a mission to a headline. Hope becomes much more interesting when you look at the actual scientific idea behind it. The mission was designed to observe Mars as a climate system, to follow the movement of water vapor and ice, to monitor atmospheric temperature, and to study how lighter particles such as oxygen and hydrogen escape into space. Suddenly, Mars is no longer just a surface covered in ancient clues. It becomes a world in the middle of a long transformation. A planet that may once have had a thicker atmosphere, warmer conditions, and liquid water on the surface now appears dry and cold. Somewhere in that transition lies one of the central mysteries of Martian science. What happened? How does a world go from potentially habitable to plainly hostile? And how much of that story can still be reconstructed from what remains overhead rather than underfoot? To answer that, we need to think about Mars not just as a place, but as a balance of forces. Here on Earth, our atmosphere feels natural to us. It surrounds us so completely that it is easy to forget it is even there. But an atmosphere is not guaranteed. It has to be held, replenished, protected, and constantly reworked by planetary conditions. Earth still has a magnetic field. Earth still has internal activity. Earth still cycles volatiles through ocean, air, rock, and life. Mars appears to have lost much of that protective and regenerative machinery long ago. Without a strong global magnetic shield, the Martian atmosphere sits far more exposed to the activity of the Sun. High-energy radiation and solar wind interact directly with the upper air. Atoms can be ionized, accelerated, and lost to space. Over immense spans of time, that loss becomes a planetary fate. Hope was built to study part of that process from a vantage point broad enough to connect lower atmospheric behaviour with what is happening higher up. That is one of the subtle strengths of the mission. It was not just measuring isolated variables, it was trying to connect layers. And that gives the mission a particularly elegant place in the modern story of Mars. Other spacecraft have looked at the surface in exquisite detail. Others have studied atmospheric loss from different orbital patterns. Hope adds something like continuity. Because it remains farther out, it can keep a global watch over the planet, tracking weather across regions and seasons, while also contributing to the study of how atmospheric particles escape. In other words, it helps make Mars legible as a whole. That phrase matters more than it might seem. A world becomes scientifically understandable not only when we gather more data, but when we gather the right kinds of data in relation to one another. You can know many facts about a planet and still not understand the logic that ties them together. Mars is full of such facts. Dry river-like channels, hydrated minerals, dust storms, polar ice, thin air, giant volcanoes, escaping hydrogen, surface frost, ancient lake beds. Each is meaningful, but the real scientific prize lies in seeing how they belong to the same narrative. That narrative begins to sharpen when we compare the Mars of today with the Mars implied by its geology. Consider the enormous valley systems and outflow channels seen in orbital imagery. They do not look like random scratches, they look like consequences. Some stretch for thousands of kilometres. Some appear to have delivered material toward lower northern regions that may once have held standing bodies of water. Others suggest catastrophic flooding rather than the gentler persistence of long-lived rivers. There is debate over the precise role of floods, glaciers, and groundwater release in shaping particular features, but the larger point remains. Modern Mars is not the Mars that carved much of that terrain. When the Indian mission looked down on features such as Valles Marineris, Kasai Valles, Ares Valles, and the broader pattern of channels cutting across the surface, it was seeing relics of a more dynamic hydrological past. Some regions show evidence that water once flowed, pooled, froze, or altered the minerals in the crust. The planet now looks barren, but its surface keeps whispering that this was not always so. That whisper becomes louder when atmospheric science joins the conversation. If Mars once had more water, it must also once have had conditions under which that water could persist more easily at the surface. That implies a different atmosphere, a different thermal regime, perhaps even a different interior state. And that is where the newer generation of missions becomes so compelling. India's orbiter gave Mars back some of its planetary grandeur. Hope pushes further by asking how that grandeur decayed. What stripped this world down? How did it lose so much of what it may once have had? And can the processes still visible today tell us how far the loss has already gone? These questions are not only about Mars. That is another reason they matter. When we study how atmospheres evolve, we are also refining our sense of planetary fragility more generally. Earth and Mars are not twins in any simple sense, but they do offer a powerful comparison. One world remained wet, magnetically shielded, and biologically active. The other seems to have cooled faster, lost key protections, and been exposed to long-term atmospheric thinning. To compare them is to ask what keeps a world alive in the broad planetary sense, and what allows that condition to fail. There is a quiet philosophical force in that comparison. Mars does not merely fascinate because it might once have hosted habitable conditions. It fascinates because it makes habitability look contingent. We live on a planet whose surface water, moderate pressures, and long climate stability are easy to experience and hard to explain in full. Mars stands nearby as a warning that such stability is not automatic. A planet can begin with promise and still end in desiccation. And yet even that outcome is not simple. Modern Mars, though harsh, is not inert. Its atmosphere may be thin, but it still circulates. Water still exists, though not in the forms most familiar to us. Dust still moves, clouds still form. The giant dust storms visible from orbit can wrap across huge stretches of the planet, obscuring the surface and altering how sunlight reaches the ground. Solar-powered rovers have learned just how consequential such storms can be. What appears from a distance as a beautiful weather pattern can become, on the surface, a threat to the survival of machinery. Then there are the clouds. On Earth, clouds are so familiar that they sometimes seem mundane. On Mars, they feel uncanny. Water ice clouds can gather over volcanoes such as Olympus Mons and Elysium Mons, where air is forced upward by topography. Seen from orbit, these formations carry a strange emotional weight. They remind us that even on a colder, thinner, more desolate world, air still rises, cools, condenses, and shapes what can be seen from above. Mars is alien, but not so alien that all meteorology has vanished from it. That interplay between the familiar and the strange is one reason orbital imagery matters so much. Consider the sight of a giant dust devil casting a long shadow across the Martian surface, or the sight of fog-like water ice filling a deep canyon system, or the pattern of dark dust apparently halted and redirected by crater rims, revealing prevailing wind over long intervals. Each image does more than decorate a mission report. Each helps us see Mars as a place where processes are still operating, where atmosphere still speaks to ground, and where the past is never entirely disconnected from the present. Even the unresolved features tell us something important. Take Orcus Patera, an elongated crater-like structure that resists easy classification. It is too unusual to fit neatly into expectations. Scientists have proposed possibilities, but no clear consensus settles the question. That uncertainty is not a flaw in the larger story. It is part of what makes Mars scientifically alive. A planet becomes truly interesting not when every feature has already been named and filed away, but when some still remain stubborn against interpretation. Mars continues to contain shapes that do not surrender themselves quickly. This is precisely why it matters that more countries are arriving there with different mission architectures and different scientific emphases. Every mission does not need to solve the whole planet. It only needs to add clarity at the right point. India helped show the whole world of Mars in sweeping, true colour perspective. The UAE moved the focus toward climate connection and atmospheric escape. Together, these missions help make Mars less fragmented. And they also demonstrate something broader about the changing character of exploration. The older model of prestige missions often encouraged singularity. One giant national effort, one dramatic goal, one iconic image. The newer model increasingly depends on complementarity. One orbiter watches globally, another samples locally. One mission maps escape high above, another drills or roves below. One detects weather patterns over time, another studies mineral traces left by ancient water. The science becomes cumulative across borders. That is a profound change in how humanity approaches other worlds. Space exploration begins to resemble a distributed inquiry, rather than a sequence of isolated national epics. A mission from one country does not invalidate the need for a mission from another. In many cases, it creates it. Once India showed a certain kind of planetary view, other forms of investigation became more interesting, not less. Once Hope began observing Mars as a weather system, it strengthened the value of comparing those findings with other orbiters, studying different layers and timescales. And through all of this, Mars becomes something else too. It becomes a test case for a future in which many nations participate seriously in interplanetary science. That future is not hypothetical anymore. It is already arriving. The old hierarchy, in which some countries were assumed to generate real planetary knowledge while others merely admired it, is becoming harder to sustain. Mars is one of the places where that old assumption is quietly dissolving. The remarkable thing is that this transformation has happened without changing the planet itself. Mars is still there, with its volcanoes, canyon scars, dust storms, thin air, lost water, and unresolved history. What has changed is us. More precisely, what has changed is who counts as part of the we that studies it. Once that question opens up, the next stage of the story becomes unavoidable, because seeing another world is one thing, touching down on one exact point of it with extraordinary precision is something else entirely. That is where Japan's recent lunar mission enters the story with such force, because precision changes the meaning of arrival. In the earliest years of lunar exploration, simply getting to the moon in one piece was an achievement so difficult that almost everything else came second. A probe could miss its intended spot by many kilometers and still be counted a success if it survived long enough to return data. In that context, the moon was treated less like a mapped destination and more like a hostile body that had to be negotiated with carefully and humbly. Engineers aimed for broad, safe regions, accepted wide uncertainty, and relied on the fact that the lunar surface, at least in some places, offered large enough plains to forgive imperfect targeting. That older approach made sense. The moon has no atmosphere to help slow a spacecraft. There is no parachute phase, no aerodynamic glide path, no forgiving cushion of air through which a lander can bleed off speed. Every part of the descent depends on propulsion, guidance, and timing. A spacecraft has to reduce velocity almost entirely through its own engines while descending toward a surface littered with craters, rocks, slopes, and shadows. Even a small error can become fatal quickly. Come in too fast and the vehicle crashes. Drift laterally at the wrong moment and it may strike unsafe terrain. Touch down with too much force and instruments can be damaged or destroyed. Lunar landing is not only difficult, it is unforgiving. That unforgiving nature shaped the first era of exploration. The Soviet Union needed repeated attempts before finally landing Lunar 9 successfully. Early American lunar programs also suffered failures before developing reliable landing capability. Even the Apollo missions, remembered now with an aura of near inevitability, were navigating danger in real time. The landing zones were chosen carefully. The lighting conditions mattered immensely. The near side of the moon offered practical advantages that constrained where astronauts could go. In effect, exploration was being conducted within a narrow corridor of manageable risk. But if you want to move beyond that corridor, precision becomes everything. A world changes once you can land not merely somewhere on it, but somewhere specific on it. That is the difference between broad reconnaissance and targeted science. It is the difference between admiring a landscape and selecting one exact rock formation within it, because that formation might answer a question about planetary history. It is also the difference between surviving on the moon and one day living there with intention. Future bases, resource extraction zones, water ice access points, scientific outposts near geologically valuable terrain, all of them depend on narrowing uncertainty. Japan's smart lander for investigating Moon, known as SLIM and widely nicknamed Moon Sniper, represented a dramatic step in that direction. The mission was not built around brute scale or grand spectacle. In some ways, that makes it even more revealing. Its purpose was focused: demonstrate precision landing, show that a compact spacecraft could descend toward a much smaller target than those accepted by earlier missions, prove that landing on the moon no longer had to mean choosing from a handful of forgiving plains. If that capability matured, a new geography of lunar exploration would open. To appreciate the importance of that, it helps to understand the concept of a landing ellipse. No spacecraft aims at a mathematical point and arrives there perfectly. Every descent contains uncertainty, and that uncertainty can be represented as an area within which the lander is expected to come down. In earlier eras, that area was large. Apollo 11, for all its historic greatness, was still operating inside a landing ellipse vast by modern standards. Decades later, improvements in guidance, sensing, mapping, and onboard computation allowed that ellipse to shrink. But shrinking it from kilometers to mere tens of meters is not a routine refinement. It is a profound technical leap. SLIM attempted exactly that kind of leap. The lander used a vision-based navigation system often referred to as smart eyes. As it descended, it continuously imaged the surface below, and compared what it saw with detailed orbital maps gathered by previous missions. This is a crucial development in the logic of exploration. The moon was no longer just being visited, it was being read in real time. The lander could look, recognize, compare, and adjust. Instead of trusting a largely pre-computed path with limited situational awareness, it could update its understanding during descent and steer toward the intended region with far greater confidence. The target zone for the mission was extraordinarily small compared with the broad landing uncertainty of the past, and by that standard, the mission achieved something remarkable. Japan became the 5th nation to soft land on the moon, and it did so with a touchdown astonishingly close to the centre of its intended zone. That result alone would have made the mission historically significant. A smaller, lighter lander had demonstrated that precise, targeted lunar arrival was no longer theoretical. Engineers had shown that a spacecraft could narrow the problem of landing from regional scale to something much closer to site-specific scale. Yet what makes the story unforgettable is that success and near disaster arrived together. During the final descent, one of Slim's 2 main engine nozzles detached at a very low altitude above the lunar surface. That is the sort of failure that can instantly cascade into catastrophe. With thrust no longer balanced properly, the lander developed lateral motion. In the final moments of descent, when every second matters and the margin for correction is vanishingly small, the spacecraft had to respond to a failure that could easily have destroyed it. And still, somehow, it did not crash outright. This is where the deeper triumph of the mission begins to emerge. The lander's systems recognized the anomaly, compensated enough to avoid total disaster, and found a survivable touchdown. It did not land upright as intended, it tipped over onto its nose. Images from one of the tiny deployed probes later showed the main body resting upside down, its solar panels oriented poorly relative to the sun. On paper, this should have transformed a precision triumph into a crippled mission, perhaps even a short-lived embarrassment. Instead, it produced something stranger. The mission was simultaneously a success, a malfunction, a survival story, and a preview of the future. That paradox is worth pausing on. In the older imagination of space exploration, missions often get divided too neatly into success and failure. But real exploration does not always obey those categories. Sometimes a mission proves its central concept while still enduring a major accident. Sometimes a spacecraft demonstrates the very resilience that will matter most in harsher future missions, precisely because it was not allowed to operate under ideal conditions. Slim landed with pinpoint accuracy, suffered a severe hardware problem, ended up upside down, and still managed to return data. Each of those facts alters the meaning of the others. Because the solar panels were not facing as planned, available power was sharply limited. Soon after landing, the mission team used what remained of the battery to capture and transmit a mosaic image of the landing area. Then they shut the spacecraft down, effectively placing Hope in geometry and time. If the changing angle of sunlight later illuminated the panels more favourably, there was a chance the lander might wake again. If not, Moon Sniper's story would end after a brief and improbable debut on the surface. What followed feels almost theatrical, but it was entirely real. Roughly 10 days later, as the angle of sunlight changed, the lander came back to life. For a short period, it resumed sending information and images. It had done something it was not supposed to be able to do in its physical state. Even this, however, looked temporary. The lunar night was approaching, and that introduced a far more brutal problem than an awkward landing posture. A day on the moon does not resemble a day on Earth. Sunlight and darkness each last around 2 weeks. With no substantial atmosphere to moderate temperature, the difference between lunar day and lunar night is savage. Surface temperatures can soar under direct illumination and plunge to extremes in darkness. Electronics not explicitly engineered for such endurance are expected to fail. Many lunar spacecraft do. Even missions that reach the moon successfully can go silent forever after a single lunar night. The environment is simply too harsh. Slim was not designed to survive a lunar night. That point is essential. This was not a mission advertised around long-term endurance through repeated thermal punishment. It was a precision landing demonstrator, and a compact science platform. After the brief recovery in sunlight, the spacecraft was placed into hibernation, with limited expectation that it would ever answer again. And then, it did. When contact was attempted after the sun returned, the lander responded. It survived one lunar night. That alone would have been startling, but then it survived another, then another. Again and again, the little upside-down spacecraft returned data and images from the moon, confounding the assumptions built into its own mission profile. It became not only a proof of precise landing, but a symbol of accidental resilience. There was something deeply revealing about that kind of outcome. Space exploration often advances by deliberate design, but sometimes it also advances through surprise. A mission built to demonstrate one capability ends up revealing another. Engineers learn not only from what they planned the spacecraft to do, but from what the spacecraft somehow manages to endure when events go wrong. In that sense, SLIM may have contributed to future exploration twice over. First, by proving that precision targeting on the moon is increasingly achievable. Second, by reminding everyone that robust behavior under partial failure conditions may matter just as much as nominal performance. The scientific implications of precise landing are substantial. A spacecraft able to reach a very small target zone can be sent to more dangerous but more rewarding terrain. Areas near crater rims, ejector deposits, mantle-exposed regions, or rocky zones once judged impractical become newly available. You do not have to land far away and hope a rover can bridge the gap. You can arrive where the science is. That reduces complexity for some missions, but more importantly, it changes mission design philosophy. Engineers and scientists gain the freedom to ask more specific questions because they are no longer forced to settle for the safest broad plane every time. The practical implications are just as important. Future lunar infrastructure will depend on this kind of capability. Water ice is thought to exist in permanently shadowed regions near the poles, but those areas are difficult to access and often surrounded by hazardous terrain. If you want to exploit such resources or establish a base near them, broad landing uncertainty becomes a serious liability. Precision is not a luxury there, it is a requirement. The same is true for missions intended to use lava tubes, crater walls, or specific sunlit ridges for power and thermal management. A mature lunar presence will be built on logistics, and logistics begins with arriving where you mean to. This is why Moon Sniper belongs to a larger story than its modest scale might suggest. It is part of the transition from exploratory visitation to intentional operation. The Moon is slowly being transformed from a body we can reach into a body we can navigate. That may sound like a subtle difference, but it is enormous. Reaching a world proves access. Navigating it precisely proves control. And control, in the engineering sense, is what turns heroic one-off missions into sustainable systems. There is also a human dimension to the mission's odd, resilient life. The upside-down lander feels strangely emblematic of the new era of exploration itself. More countries are reaching space. More missions are being attempted with narrower margins and more specialized goals. Not every success will look clean. Some will arrive battered, compromised, half-broken, and still transformative. Exploration is not becoming simpler because more nations are doing it. If anything, it is becoming more ambitious, more distributed, and more technically varied. That means the story of success is going to look messier and perhaps more interesting than before. By surviving and continuing to operate after such an improbable sequence of events, Slim helped redefine what a small national mission can mean. It did not need to rival Apollo in scale or drama to alter the trajectory of lunar exploration. It only needed to prove that one narrow capability, precision, was now sufficiently real to change the planning horizon of everyone else. And once that happens, the Moon is no longer just a place where landers attempt survival. It becomes a place where future missions may choose exact destinations for exact reasons, where even more unlikely national stories begin to make sense, and where some of the most revealing chapters in space history may belong not to the loudest powers, but to the ones that endured quietly long enough to change the rules. That quiet power becomes even clearer when we leave the worlds of Mars and the Moon for a moment and look back at Earth. Because some of the most revealing space stories are not about what a mission discovered overhead, but what the mission meant to the nation that launched it. Space programs are often described in the language of capability, payload, orbit, thrust, and cost. All of that matters, but beneath the engineering there is always another layer. Spaceflight is also about self-image. It is about what a country believes it can build, what future it thinks it deserves, and whether it sees itself as a participant in history or merely as terrain on which history happens. Few examples illustrate that more poignantly than Britain's Black Arrow program and the satellite Prospero. It is a story with an odd emotional texture because it contains genuine technological achievement wrapped inside national hesitation. Britain did, in fact, become one of the few nations to launch a satellite into orbit using a rocket of its own making. Yet the launch arrived at the very moment the country had already decided to abandon the capability that made it possible. In other words, Britain proved it could do the thing just as it chose not to keep doing it. That gives the story a bittersweet quality almost from the start. In the early decades of the space age, Britain was not ignorant of the significance of rockets. It had technical talent, industrial depth, and scientists who understood that launch capability mattered. Earlier rocketry work had been tied closely to military aims, but the emerging vision was broader. A domestic rocket could place satellites into orbit for communication and scientific use. It could allow Britain to remain not merely a consumer of other nations' launch systems, but an independent actor in space. That was the hope that animated the development of Black Arrow. The rocket itself was not enormous by the standards that would later define superpower space programs, but it did not need to be. It was designed for a specific class of orbital mission, and in that role, it was a serious engineering project. Its parts were built across Britain, assembled through a distributed national effort, and eventually sent to Australia for launch. Even that detail says something important. Geography, politics, empire, and logistics were all entangled in the story. Britain's access to launch was already shaped by the world it had made and the world it was becoming. But the political environment was not favourable. Governments do not fund technology in an emotional vacuum. They compare programs, weigh costs, worry about prestige, and imagine economic return. In Britain's case, other priorities competed heavily for attention, and the Black Arrow program entered that struggle with a disadvantage. It was expensive enough to attract skepticism and not politically spectacular enough to guarantee protection. Worse still, it suffered technical setbacks. The first launches did not go smoothly. Failures and delays accumulated. Each one made it easier for a cautious government to argue that the nation should step back and buy launch services elsewhere, rather than continue paying to cultivate its own. This is a familiar pattern in technological history. Capabilities are not always lost because they are impossible. Sometimes they are lost because they are awkwardly timed. A program can be viable in principle and still politically vulnerable in practice. Black Arrow lived inside that vulnerability. By the time the rocket finally succeeded, the decision to cancel the wider effort had already been taken. That is what makes the launch of Prospero in 1971 so affecting. The fourth Black Arrow had already been built. It was allowed to fly, and when it did, it worked. Prospero was placed into orbit, making Britain the sixth nation to launch a satellite on its own rocket. But the triumph came with an almost immediate sense of finality. This was not the beginning of a national launch tradition. It was the coda. There is something almost literary about the name change that accompanied the satellite. It had originally been called Puck, continuing a tradition of Shakespearean names associated with air, playfulness, and lightness. After the cancellation of the program, it became Prospero. That choice feels revealing. Prospero, the magician who gives up his powers, is a far sadder symbol than Puck. The name captures the mood perfectly. A technical magic had been achieved, then set aside. The country had proven a capability, and then relinquished it. This does not mean the mission was meaningless, quite the opposite. Prospero still flew, it still operated, it still taught British scientists about satellite design, and in time its story acquired an afterlife no one at the moment of cancellation could have fully predicted. Long after its launch, as the commercial and strategic value of smaller space systems grew, Britain found itself drifting back toward launch capability. New companies looked at old designs. Black Arrow, once shelved as a dead end, began to look oddly well suited to later needs. History had not erased the effort, it had simply delayed its relevance. That reversal matters because it reminds us that space history is full of unfinished lines. Not every cancelled program is merely a failure. Sometimes it becomes a seed. The technical knowledge accumulates quietly. The symbolism persists. The lost capability remains part of national memory, waiting for conditions to change. Prospero itself, still orbiting for decades after going silent, became a strangely fitting emblem of that suspended legacy. Not gone, not active, just waiting overhead, as if history had placed a bookmark in the sky. If Britain's story is bittersweet because it succeeded and stopped, Zambia's is fascinating for almost the opposite reason. It barely possessed the material prerequisites for a real space program at all, and yet it remains unforgettable because of what it dared to imagine. In the 1960s, as the United States and the Soviet Union battled for dominance in orbit and on the moon, Zambia had just emerged from colonial rule. It was a new nation, still defining itself politically and institutionally. And in that fragile moment, one of the most unusual figures in space history announced an astonishing ambition. Zambia, too, would go to space. At the centre of that story stands Edward Makuka Nkoloso, a school teacher, anti-colonial activist, and founder of what he described as a Zambian space effort. His plans were extravagant, theatrical, and by ordinary engineering standards, absurd. He spoke of sending Zambian astronauts, or Afronauts, to the moon, and even to Mars. There were training exercises involving rolling recruits downhill in oil drums, swinging them on ropes to simulate weightlessness, and teaching techniques that had little basis in real astronautics. The rockets themselves existed more in rhetoric and rough improvisation than in any credible launch architecture. To describe these details plainly is not to mock the story. The strangeness is part of what makes it important. The question is not whether Nkoloso's program was technically viable. It was not. The question is what exactly he was doing when he spoke that way, posed that way, and invited the world to look. There are several possible answers, and the uncertainty is part of the fascination. One possibility is that he was, at least in part, serious. Not in the sense of having a plausible path to Mars, but in the sense of genuinely believing that Zambia and Africa should not accept a permanent position outside scientific modernity. For a newly independent nation, speaking in the language of spaceflight might have been a way of refusing inherited limits. Colonial rule had not only extracted resources and denied political autonomy, it had also shaped expectations about who counted as advanced, rational, inventive, and future-oriented. To declare a Zambian path to the stars, however improbable in practical terms, was to reject that hierarchy. Another possibility is that the whole project functioned as satire, or at least as political theatre with a sharpened edge. Nkoloso's remarks often contained barbs aimed at imperial powers. His rhetoric had a way of exposing the absurdity of prestige competition by exaggerating it. The fact that he spoke of sending a missionary to Mars while warning that Christianity should not be forced on Martians if they did not want it feels less like naivety than pointed commentary. In that line alone, colonial history is being mirrored back at the colonial powers in comic miniature. Perhaps the most likely truth is that the story lived somewhere between those modes. It was part aspiration, part satire, part performance, part nation branding, part anti-colonial declaration, and perhaps part attempt to inspire the young people around him with a vision too large to ignore. It is entirely possible that Nkoloso understood the impossibility of what he proposed in technical terms, while still believing in the cultural usefulness of proposing it anyway. That ambiguity is precisely why the story matters. Space history is usually written through hardware: launch vehicles, missions, budgets, telemetry. Zambia's almost impossible program reminds us that there is another history running alongside that one, a history of symbolic claim. Who gets to imagine themselves in the future? Who gets to speak as if the heavens are available to them too? Who gets dismissed as unserious the moment they do? For countries emerging from colonial domination, those questions are not trivial. The global order had been structured for centuries around who commanded technology and who was expected merely to receive its consequences. To step into the discourse of space was to challenge that arrangement, even if the challenge came in eccentric form. And Colosso may never have built a rocket that could reach orbit, but he did something else that matters historically. He inserted Zambia into the imaginative geography of the space age. And that insertion was not meaningless. International media noticed. Reporters came. The story circulated. In a world where newly independent African nations were often ignored unless they appeared in the context of crisis, violence, or developmental failure, the image of Zambia reaching for the moon forced a different kind of attention. Even if some of that attention was amused or condescending, it still disrupted the usual frame. Here was a country refusing smallness. There was also a more intimate way to read the story. Even if the project never had practical momentum, it may still have given its participants something rare and real. To be told, as a young person in a newly independent country, that you belong in the future rather than outside it, that too has power. Not all historical acts are measured in orbit achieved or payload delivered. Some are measured in the temporary rearrangement of possibility. Seen together, Britain and Zambia form a striking contrast. Britain had the technical means to join the launch-capable nations and then stepped away just as it succeeded. Zambia lacked those means almost entirely, but made a bold symbolic leap into the space age anyway. One story is about relinquished capability, the other is about claimed possibility. Both reveal that space exploration is never only technical, it is always braided with memory, ambition, pride, and national self-understanding. And once you begin to see that, the wider history of global spaceflight looks different again. Countries do not approach space from identical historical positions. Some inherit industrial infrastructure, some inherit trauma, some inherit both. Some use space to confirm their place among great powers. Some use it to announce that they refuse to stay peripheral. Some are building actual launch systems, others are building narratives of belonging. In both cases, space becomes a site where identity is negotiated. That does not make the engineering less important, it makes it more human. The rocket, the satellite, the training exercise, the impossible speech, all of them become expressions of what a society thinks it is doing when it reaches upward. And as the scale of missions increases in the modern era, as nations collaborate on more complex spacecraft and aim farther into the solar system, that tension between technical reality and national meaning does not disappear. It becomes more intricate, because now the future of exploration depends not only on who can imagine greatness, but on who can gather enough people, institutions, money, and patience to turn imagination into hardware. Turn imagination into hardware, and suddenly space exploration reveals its most humbling truth. No one man builds a spacecraft, no single engineer, no solitary laboratory, no lone visionary standing beside a blueprint can carry a mission all the way from idea to launch. By the time a probe leaves Earth, it already contains years of negotiations, failed tests, revised designs, institutional compromises, and the accumulated labour of hundreds or even thousands of people who may never be remembered by name. We tend to speak of missions as if agencies launch them whole, as if a country decides and a rocket simply rises. But between decision and departure lies one of the most demanding human processes in modern science, and few missions make that clearer than the Jupiter Icy Moons Explorer. At first glance, the mission sounds almost abstractly grand. A spacecraft heading toward Jupiter and its great icy moons, Callisto, Europa, and Ganymede, in search of clues about hidden oceans and the possibility that habitable environments may exist beneath frozen crusts. The destination alone is enough to inspire awe. Jupiter lies far from the warmth of the inner solar system. Its moons move through an environment drenched in radiation and dim sunlight. Any spacecraft sent there must survive a journey measured not in months but in years, then remain capable enough on arrival to carry out serious science around some of the most intriguing worlds in the solar system. But before any of that could happen, the mission had to be imagined in workable terms. That is where the real difficulty begins. Scientific curiosity by itself is not a spacecraft. It has to be translated into instruments, priorities, weights, materials, testing schedules, procurement chains, and budgets. In the case of the Jupiter Icy Moons Explorer, the European Space Agency selected the mission in 2012 as its major large-class project for the period ahead. Even that decision, which sounds final when summarized in a sentence, was only the beginning of a much longer negotiation between ambition and reality. What exactly should such a mission do? That question may sound straightforward, but in planetary science it rarely is. Jupiter's icy moons offer too many possibilities. If subsurface oceans exist under their frozen shells, what do we most need to know about them first? Should the mission prioritize internal structure, surface composition, magnetic environment, habitability indicators, ice shell thickness, geological history, or interaction with Jupiter's immense magnetosphere? Every answer to that question implies a different spacecraft. Instruments are not neutral passengers, they define what a mission can become. So the spacecraft had to be designed around a scientific logic. Cameras would be needed, yes, but cameras alone would never be enough. Spectrometers could identify surface compounds and trace what kinds of materials coat the ice. A laser altimeter could help map topography and surface form with great precision. A magnetometer could read the magnetic environment and offer indirect clues about conductive subsurface oceans. Plasma and particle detectors could characterize the charged environment around Jupiter. Perhaps most evocative of all, an ice-penetrating radar system could look below the surface itself, searching for structures hidden under kilometers of ice. Once you start listing requirements like that, the mission stops sounding like a simple probe and starts sounding like a negotiation among competing forms of knowledge. Each instrument consumes space, mass, power, data rate, and engineering attention. Each must be protected, calibrated, integrated, and justified. The final spacecraft becomes a kind of physical argument about what matters most. And then comes the next complication. No one country was doing this alone. The mission involved numerous European nations, along with contributions from beyond Europe as well. Companies, research institutes, national agencies, component suppliers, test facilities, and scientific teams all had to mesh. This is one of the least visible but most consequential features of modern exploration. We often speak of international collaboration in warm, moral terms, as if it were merely an expression of goodwill. Sometimes it is that. But on the ground, and long before a mission reaches the ground of another world, collaboration is also an engineering condition. A single spacecraft may be physically assembled in one place while embodying design work, materials, instruments, and expertise from many others. That makes such missions impressive in a different way than the older national epics of the space race. The earlier age often dramatized singular political will. A president announces, a nation mobilizes, a rocket flies. The newer model is more distributed and in some respects more fragile. It depends on coordination across institutions that do not share the same language, administrative culture, industrial rhythm, or political clock. If a modern deep space mission succeeds, it is not just because physics allowed it, it is because organization did. The Jupiter Icy Moons Explorer demanded exactly that sort of organization, because its environment would be punishing from the beginning. Jupiter is far from the Sun. That creates an immediate paradox for spacecraft design. Solar power still works out there, but far less generously. Sunlight at Jupiter is only a small fraction of what reaches Earth. To run a probe on solar arrays that far from the Sun, you need extremely large panels. So the spacecraft had to carry vast wings of solar cells, far larger than what many people imagine when they picture a planetary mission. Those panels had to unfold correctly, survive the journey, and keep generating power in dim light year after year. Yet power was only one side of the challenge. Jupiter's environment is also flooded with radiation. Sensitive electronics, instruments, and internal systems can be degraded or ruined if not protected properly. So the probe had to be shielded. At the same time, it had to avoid creating interference for its own scientific equipment. A spacecraft trying to measure magnetic conditions cannot simply be allowed to drown out its own sensors with stray magnetic noise. In other words, the craft had to be both robust and quiet, strong enough to survive, subtle enough to listen. Then there was temperature. On its way outward, the spacecraft would not travel through a uniform thermal environment. It would encounter a complex route involving gravity assists, including a pass by Venus. That meant it had to tolerate both relatively hot and deeply cold conditions during different phases of its journey. Designing a machine that can remain reliable through such thermal variation is not trivial. Materials expand and contract, surfaces heat unevenly, components age, lubrication, insulation and structure all become part of the same puzzle. Space is not simply cold, it is variable in ways that punish complacency. And as if all of that were not enough, there was still the matter of planetary protection. If a spacecraft is headed toward worlds that may contain subsurface oceans, perhaps even environments remotely compatible with life, extraordinary care must be taken to ensure that Earth organisms are not delivered there accidentally. This means clean rooms, sterilization procedures, handling protocols, and design choices all have to be treated with unusual seriousness. The irony is striking. Before we can search for alien habitability, we have to make sure we do not bring our own biosphere with us by mistake. It took years before these demands stabilized into an actual design. Only then could the spacecraft begin to become real. And when it did, its reality was scattered across Europe. The chassis came together in Spain. Other systems were integrated elsewhere. Thrusters, booms, instruments, antennas, and structural components each had their own routes through production and testing. This kind of distributed birth is characteristic of modern missions. A spacecraft does not emerge from one heroic workshop. It is assembled out of journeys. Some of the most revealing steps in that process came during testing. Testing is where the romance of exploration meets engineering suspicion. It is not enough to believe that a design should work. It has to be punished in conditions that resemble, as closely as possible, what it will actually face. That means thermal vacuum chambers, vibration tests, deployment rehearsals, communications trials, structural evaluation, and repeated checks for interactions among systems that look perfect on paper, but may misbehave in reality. One of the mission's most fascinating instruments was its radar for icy moon exploration, a remarkably long boom designed to peer through ice and reveal hidden structures beneath. Even thinking about such an instrument evokes the mission's scientific ambition. Beneath the frozen surfaces of Jupiter's moons may lie oceans larger than all of Earth's combined. To investigate them indirectly, the spacecraft needed to carry a device capable of reading layers and interfaces under kilometers of crust. But a long instrument like that must also survive launch loads, function correctly after deployment, and avoid becoming an engineering liability. So it had to be tested with care, including in unusual ways that simulated mission conditions as realistically as possible. Elsewhere, temperature extremes were recreated in giant test chambers. The spacecraft, or its components, would be frozen down toward deep space conditions, then heated from one side to imitate the harsh asymmetry of solar illumination. That alone gives you some sense of how strange space engineering really is. On Earth, we are used to designing for weather. In space, you design for vacuum, radiation, silence, thermal imbalance, and years of autonomous endurance. A probe that fails after a few hours can sometimes still teach you something. A probe that must cruise for nearly a decade before reaching its destination has to be built with a different philosophy altogether. It must be less like a machine that operates and more like a machine that persists. As more of the mission came together, the scale of the spacecraft became easier to grasp. The structure was large. The propellant load was immense. Like many deep space missions, much of its total mass at launch was not the science itself, but the means to keep redirecting that science through the solar system. Gravity assists would help, but propulsion still mattered. The mission would rely on a careful dance of celestial mechanics, using planetary flybys to shape a path outward to Jupiter over many years. Even this reminds us that a deep space mission is not a single act of launch. It is an extended conversation with gravity. When people speak casually of a mission launching on a certain date, they are often compressing an absurd amount of prior work into one dramatic moment. In the case of the Jupiter Icy Moons Explorer, by the time the rocket finally rose, the spacecraft had already lived a rich terrestrial life. It had been weighed, wired, shielded, shaken, frozen, heated, unfolded, packed, inspected, moved from country to country, and scrutinized in rooms built precisely because ordinary rooms were not pure enough for its purpose. It had already toured factories and laboratories like a traveller gathering identity before departure. And then, at last, came the transfer to the launch site. Even that is not merely transport, it is another threshold. A spacecraft leaves the spaces where it was designed and assembled and enters the place where it will be joined to the rocket that must lift it free of Earth. There, the years of distributed labour finally begin to converge physically. The launch vehicle, another masterpiece of engineering and coordination, becomes the temporary partner of the probe. For a brief interval, the mission is no longer just an object of scientific intention. It is a fully integrated event waiting for ignition. When the rocket carrying the Jupiter Icy Moons Explorer finally launched in 2023, the moment looked as all launches do from a distance: bright, sudden, irreversible. But that visible event was only the second half of the beginning. The first half had taken place in design reviews, clean rooms, test chambers, industrial workshops, software validation, international meetings, and the long patience required to keep a fragile agreement between science and hardware intact. Seen that way, the launch was less an isolated triumph than a release. Years of work, finally allowed to leave. That perspective changes how we think about modern exploration. It is tempting to narrate the history of space through destinations alone: Mars, Moon, Venus, Jupiter. But the road to those places begins far earlier, in the human problem of building something that can survive the distance. And as missions become more international, more instrument-rich, and more technically ambitious, the craft themselves start to embody a quiet truth about the civilization that builds them. No single nation, company, or heroic figure truly owns such a mission in the old mythic sense. The spacecraft is already a small multinational world before it ever visits another one. Which in turn brings us back to the deeper point running beneath all these stories. The modern age of space exploration is not only more crowded than the old one, it is more entangled. Nations still compete, certainly. Prestige still matters, flags still matter. But the hardware now tells a more complicated story. Cooperation is built into the structure of many of the most sophisticated missions. Expertise is distributed, infrastructure is shared. Scientific questions exceed national boundaries. A spacecraft bound for Jupiter may be launched by one agency, built by one company, instrumented by many nations, and interpreted by researchers across the world. In that sense, the machine becomes a rehearsal for something larger, a way of practicing what a truly planetary civilization might look like when it turns outward together. And yet even that shared outward turn depends on one more thing. It depends on being able to see worlds properly once we reach them. Because building a spacecraft is only the first challenge. The second is learning how to look through, beneath, and beyond what a planet or moon first appears to be. No nearby world teaches that lesson more dramatically than Venus. Venus has always occupied a strange place in the human imagination. It is bright enough to command attention and close enough to feel almost familiar. Yet everything we have learned about it has made it seem less like a sister world and more like a warning written in fire. From Earth, for most of human history, it looked simple enough. A brilliant object at dawn or dusk, beautiful and unreachable. But the more closely we studied it, the more it refused simplicity. Beneath its clouds lies a planet at once hidden and overexposed, wrapped in reflective haze, scorched by an overwhelming greenhouse effect, and pressurized to levels that would crush most machines in short order. If Mars invites us to imagine a lost, habitable world gone cold, Venus confronts us with something equally unsettling. A nearby planet similar in size to Earth that became almost unimaginably hostile. That transformation did not reveal itself all at once. Early on, Venus could easily absorb fantasy. Its thick cloud cover concealed the surface completely in visible light, which meant speculation flourished in the absence of direct evidence. Only with the arrival of spacecraft, especially during the Cold War, did the real Venus begin to emerge. And what emerged was not one revelation, but a layered descent into strangeness. The Soviet Venera missions played a central role in that unveiling. Many of the early attempts failed, which is worth remembering because Venus is one of those destinations that punishes even minor misjudgment. Reaching it is difficult. Entering its atmosphere in controlled fashion is harder. Surviving even briefly on the surface is harder still. Yet through persistence, Soviet engineers and scientists began to peel away the mystery. They sent probes into the atmosphere, then eventually to the ground itself. And in doing so, they changed Venus from a glowing enigma into one of the most physically vivid planets we know. To understand why Venus is so revealing, it helps to imagine the descent. Not metaphorically, but almost physically. A spacecraft approaches from above and begins falling into a world that does not yield its secrets in the familiar way. High in the atmosphere, the conditions are not yet utterly alien. The air is thin relative to what lies below. The temperatures at the upper edge are cold, but composition already hints at the deeper truth. Carbon dioxide dominates, not as a trace gas in a life-bearing atmosphere, but as the substance of the atmosphere itself. As the probe drops farther, the famous cloud deck appears. This is the layer most strongly responsible for the planet's pale yellowish appearance in visible light. These are not water clouds. They are made largely of sulfuric acid droplets, suspended in a dense chemical system that feels less like weather in the earthly sense and more like a planetary-scale industrial reaction. At these levels, winds move with astonishing speed, circling the planet far faster than the planet itself rotates. Venus turns slowly, but its upper atmosphere races around it. That alone would make the world meteorologically strange, yet it is only the beginning. Below the cloud tops, the greenhouse reality of Venus takes hold with full violence. Carbon dioxide does what greenhouse gases do, but here the effect is amplified to a planetary extreme. Heat enters, heat struggles to escape. Over immense spans of time, the planet settles into a state where surface temperatures climb high enough to melt lead. Pressure at the ground becomes crushing, comparable to what would be experienced deep under Earth's oceans. A descending probe enters a place where atmosphere no longer feels merely gaseous in the ordinary sense. Density becomes part of the experience. The air is thick enough that movement through it begins to feel conceptually closer to movement through fluid. That is one of the most startling things about Venus. It is not simply hot, it is oppressive in every variable that matters. Heat, chemistry, pressure, and duration all work together against survival. The Venera probes that reached the surface did not endure for long. They could not, but they endured long enough to send back measurements and, in some cases, the only direct surface photographs we have ever received in visible light from that world. Those images remain remarkable. After all the clouds, all the infernal atmosphere, all the conceptual scale of Venusian violence, the surface itself appears almost eerily plain. Rocks, flat terrain, a yellowish light filtered through the dense air. There is no ocean, no vegetation, no dramatic weather visible from the ground at that instant. The scene is desolate rather than theatrical, and perhaps that makes it even more unsettling. This is not a fiery fantasy landscape in constant eruption. It is a dry, oppressive plain under conditions so extreme that ordinary geological stillness becomes lethal. Yet if visible light gives us that brief, haunting glimpse, it also demonstrates one of the central lessons Venus teaches about planetary science. Visible light alone is not enough. In fact, visible light is one of the worst ways to understand Venus globally, because the clouds conceal almost everything that matters most. To really see the planet, scientists had to turn to other parts of the electromagnetic spectrum. Infrared observations transform the picture. In infrared, heat itself becomes readable. The lower atmosphere glows with thermal intensity. The contrast between hot depths and higher cloud structures becomes vivid. Sulfuric acid clouds appear as darker features over a brighter, hotter background beneath. Suddenly the atmosphere is no longer just a veil. It becomes layered, dynamic, and legible in a new way. What visible light had flattened into a pale planetary disk now opens into bands, structures, and thermally distinct regions. This matters scientifically and philosophically. It reminds us that a planet is never just what it looks like to human eyes. Human vision evolved for a small set of terrestrial conditions. Other worlds often refuse to disclose themselves on those terms. Venus in particular almost seems to demand technological extension before it can be understood. We must look in wavelengths we do not naturally see. We must accept that some realities are only available through instruments. In that sense, Venus is one of the clearest demonstrations that modern astronomy is not simply enhanced vision, it is transformed perception. Ultraviolet observations complicate the story even further. In ultraviolet, the cloud tops of Venus display contrasts and patterns not obvious in visible light. Darker streaks and blotches appear where something in the atmosphere absorbs ultraviolet radiation. Yet even now, scientists still debate exactly which chemicals are responsible for some of these patterns. That lingering uncertainty is important. Venus has been studied for decades by probes, orbiters, radar mappers, and telescopes, and still it refuses complete chemical transparency. The planet keeps part of its atmospheric identity concealed. There is also the matter of the polar vortices. Infrared imaging has revealed vast, unusual vortex structures near the poles of Venus, complete with multiple eyes and rapidly changing form. These are not simple equivalents of terrestrial hurricanes. They belong to a climate system governed by different balances of rotation, circulation, chemistry, and thermal structure. Their behaviour is difficult to model. They shift on short timescales. They remind us that Venus is not merely static hell. It is an active atmospheric machine, complex enough to resist full description. And then there is radar, perhaps the single most powerful tool ever used to reveal the hidden geography of Venus. Because radio waves can penetrate the thick clouds far better than visible light, radar mapping allowed scientists to reconstruct the planet's surface from orbit. What emerged from those maps was extraordinary. Volcanoes, lava plains, vast tectonic-looking features, impact craters, chasms, rises, and deformational structures all came into view. A world that had seemed blank from afar became richly sculpted. The surface was not only visible now, it was geologically expressive. This is where Venus becomes especially interesting in comparison with Earth. It is often called Earth's sister planet because of its similar size, and in one narrow physical sense that is true. But as soon as you move beyond bulk size, the similarities begin to fracture. Venus seems to have followed a radically different evolutionary path. It does not have oceans. It does not appear to have plate tectonics operating in the earthly sense. Its atmosphere is overwhelmingly carbon dioxide. Its greenhouse effect is runaway in a way Earth has never experienced. Yet the surface shows immense volcanic influence, suggesting a world with its own internal dynamism and thermal history. That divergence raises one of the deepest questions in comparative planetology. How do two rocky planets of roughly comparable size end up so radically different? Why did Earth remain clement enough for persistent liquid water, climate moderation, and life, while Venus crossed into an almost irreversible hothouse state? Somewhere in that divergence lies a lesson, not just about Venus, but about Earth and about rocky planets more generally. This is one reason Venus has re-emerged as such an important scientific target after years of relative neglect. For a while, Mars tended to dominate public imagination because it seemed more hospitable, more accessible, and more closely tied to the question of past or present life. Venus, by contrast, seemed like a planet already explained in broad outline. Hot, high pressure, carbon dioxide rich, end of story. But that outline turns out to conceal tremendous scientific richness. Venus is not merely an example of a greenhouse disaster. It is a world whose atmospheric chemistry, geological resurfacing history, cloud structure, circulation, and possible ancient habitability are still not fully understood. Even the controversial phosphine episode showed something useful, regardless of where the final truth lands. When some observations suggested traces of phosphine in the Venusian atmosphere, excitement surged because phosphine can, in certain contexts, be associated with biological activity. The claim was challenged, questioned, partly withdrawn, then revived in modified form. In one sense, this is simply how science works. Observations are made, scrutinized, contested, and reinterpreted. But in another sense, the episode reminded the wider world that Venus is still capable of surprising us. the planet remains scientifically unsettled enough that even a disputed chemical signal can reopen major conversations. And that possibility, however uncertain, is thrilling. Not because Venus is likely to host floating cities or cinematic life forms in its clouds, but because it reminds us that planets are often less finished than our summaries of them. We say Venus is dead. We say Venus is hellish. We say Venus is understood. But then new instruments, new models, or new spectra arrive, and suddenly the certainty frays. The real world proves more layered than the textbook phrase. That layered reality is exactly why Venus belongs in this broader story of modern exploration. It shows how new technologies and new missions can return to a familiar world and make it unfamiliar again. It also shows how knowledge accumulates across generations and across nations. Soviet landers gave us the first direct contact. American radar missions mapped almost the whole surface. Later spacecraft from Europe and Japan added atmospheric and thermal insights. Future missions from multiple countries aim to continue that work. No one mission exhausts Venus. The planet keeps requiring another angle. In that sense, Venus is almost the perfect emblem of the modern age of planetary science. It cannot be understood from one orbit, one wavelength, one nation, or one era of instruments. It requires stacking perspectives until the hidden world begins to emerge through the haze. And once we accept that kind of layered seeing as the new normal, it becomes easier to understand why the future of space exploration is no longer defined only by who can get somewhere first. More and more, it is defined by who can sustain attention, build infrastructure, revisit difficult questions, and decide what kind of long-term presence they intend to have in space at all. Because once you stop asking only how to see a world, and start asking who will shape the larger map of exploration in the decades ahead, the conversation moves from atmospheric chemistry and radar echoes to something even more consequential: the political architecture of the future solar system, and the nation now most determined to redraw it. And no nation has pushed itself more insistently into that future conversation than China. For much of the 20th century, China was not perceived as a central space power at all. It had ambition, certainly, but ambition alone does not lift payloads into orbit. The country's early decades under communist rule were marked by political upheaval, economic disruption, and campaigns that deeply damaged the scientific and intellectual environment needed for complex technological development. The Great Leap Forward devastated the economy. The Cultural Revolution turned suspicion against many of the very people whose expertise would have been essential to sustained scientific growth. If you looked only at those decades, it would have been difficult to imagine China eventually becoming one of the defining forces in the modern space race. But that is the danger of reading history too close to one moment. Nations can change quickly when industrial capacity, state priority, education, and long-term planning begin to align. Over the last several decades, China has undergone one of the most dramatic economic expansions in modern history. That expansion has not only altered manufacturing and trade, it has also changed what kinds of scientific and engineering projects the country can realistically sustain. Space exploration, once a symbolic aspiration at the edges of national capability, has become one of the clearest arenas in which China intends to demonstrate maturity, confidence, and strategic depth. One reason this matters so much is that China is not simply repeating the path of earlier powers. It is entering an already populated space age with full awareness of the infrastructure, legal tensions, prestige value, and practical opportunities that now define exploration beyond Earth. In some areas, this allows China to move with remarkable focus. It can observe what worked for others, what stalled, what became too expensive, and where symbolic firsts still remain available. It is not starting at the beginning of the story. It is joining late enough to learn from the first chapters and early enough to shape the later ones. The Moon provides perhaps the clearest example. China's Chang'e program began with orbiters, then progressed to landers, rovers, and sample return missions. That progression alone would already be impressive. It shows disciplined capability building, each mission adding complexity rather than leaping recklessly beyond what has been demonstrated. But China also pursued targets that carried special significance. Landing on the far side of the moon was one such move. The far side cannot communicate directly with Earth, which means the mission required relay infrastructure and careful systems architecture beyond the landing itself. To accomplish that first was not just technically impressive, it signaled something important about strategic thinking. China was not content to follow established lunar routes. It wanted to enter territory where genuine distinction remained possible. That pattern continued with sample return missions. Returning lunar material to Earth is not only a symbolic act, it is a scientific one. Laboratory instruments on Earth are vastly more capable than anything that can be miniaturized onto a rover or lander. Samples can be studied repeatedly, with improved methods by new generations of scientists. To bring them home is to extend the moon into terrestrial laboratories. It also has obvious long-term implications for countries interested in learning how to use extraterrestrial materials, plan off-world infrastructure, or simply demonstrate end-to-end mission sophistication. And the moon is only the beginning. China has made no secret of its broader ambitions. It has reached Mars with Tianwen-1 and the Zhurong rover, becoming the second nation to place a rover successfully on the Martian surface. That achievement matters not only because Mars is difficult, but because China managed the mission as a combined orbital and surface effort. Zhurong then went on to study the terrain and subsurface structure around its landing site, contributing to our picture of Martian geology and the possible history of water. This is worth emphasizing because it shows a recurring feature of China's space program. The country does not only seek headline moments, it also seeks the scientific credibility that must follow if those moments are to count as more than spectacle. At the same time, it is impossible to separate China's space trajectory from geopolitics. The United States has long viewed technological leadership in space as strategically significant. It is not just about science. It is about launch systems, satellite architecture, communication infrastructure, surveillance, prestige, industrial competence, and long-term influence over the rules governing activity beyond Earth. American law has at times sharply limited cooperation with China in space on the grounds of national security and technology protection. That constraint has helped create a peculiar situation. Scientists in both countries may often have reasons to value cooperation, yet the political framework around them pushes toward parallelism, suspicion, or rivalry. The result is that China has been compelled, and in some ways motivated, to build more of its own independent infrastructure. Tiangong, its space station, is a clear example. Excluded from the International Space Station framework, China built a smaller but fully functional station of its own. The significance of that should not be underestimated. Space stations are not merely habitats in orbit, they are statements of permanence, logistical maturity, and institutional continuity. To maintain one is to demonstrate that your space program can operate not just in bursts of mission drama, but in ongoing cycles of launch, docking, crew rotation, maintenance, and experiment. Tiangong also matters because it reveals how the second great age of space infrastructure may unfold. Unlike the earlier era, where the International Space Station stood as a uniquely cooperative flagship, the future may contain multiple orbital ecosystems. Some may overlap, some may compete, some may invite different clusters of partner nations into their own networks of scientific participation. China has clearly signalled that it wants to build such a network. Its invitations to other countries to participate in lunar and orbital projects are part diplomatic outreach, part practical alliance building, and part statement that the future architecture of space need not be written exclusively in Washington. This becomes even more significant when we look at China's plans for the moon. The proposed International Lunar Research Station, pursued with partners including Russia and others, is not yet a finished reality, but the concept itself is powerful. It suggests a future in which the moon becomes organised not around one globally shared framework, but around partially overlapping blocks of infrastructure, standards, and political loyalty. The United States has its Artemis Accords and its own emerging lunar vision. China has its parallel effort. The language may emphasize science and openness, and much of that language is sincere, but the strategic undertone is difficult to ignore. Lunar infrastructure is never just lunar infrastructure. It is the beginning of a political footprint beyond Earth. And then there are the rockets. Deep space ambition depends on lift capacity. You can have plans for lunar bases, Mars sample returns, large telescopes and orbital constellations, but without strong launch systems, those plans remain fragile. China's work on the Long March family, and particularly its long-term pursuit of much heavier and more capable launch vehicles, shows that it understands this perfectly well. Reusability too has entered the equation. The global launch market is changing under pressure from lower costs and more rapid turnaround, and China is clearly unwilling to allow others to define that new normal unchallenged. This connects to something larger than exploration in the narrow scientific sense. Space is increasingly economic. Communications, Earth observation, navigation, remote sensing, launch services, in-orbit manufacturing, resource extraction proposals, and mega-constellations all point toward a future in which access to space is woven into civilian and military power more deeply than ever before. China's plans for large satellite networks and long-term logistics architecture across the solar system should be read in that context. Even if some of the most expansive visions remain far from implementation, the fact that they are being discussed at all reveals the scale at which Chinese planners and scientists are willing to think. None of this automatically means China will overtake the United States as the dominant space power. That conclusion is often stated too simply. The United States still spends far more on space overall. Its launch ecosystem is broader. Its commercial sector is more mature in many areas. Its scientific institutions remain extraordinarily productive. But budgets do not tell the whole story either. China can often build and launch at lower cost. Its political system can sustain certain long-term projects with less visible public negotiation. And prestige-driven national programs do not always need to exceed another country's total output in order to alter the strategic balance. Sometimes they only need to succeed in a few key domains at the right moment. That is what makes the current phase of the story so interesting. It is not a replay of the Cold War, but neither is it a serene age of universal cooperation. It is something more complicated. Scientific goals coexist with strategic anxieties. Invitations to collaborate coexist with legal restrictions. Parallel lunar architectures begin to form, while researchers across borders still often share a common curiosity about the same rocks, the same moons, the same plasma environments, the same planetary histories. The tension is real and unresolved. In a sense, space is becoming more like the rest of the world. Infrastructure matters. Standards matter. Access matters. Narrative matters. So do alliances. The difference is that in space, these issues are only now beginning to harden into long-term structures. We are still in the formative phase. The rules that govern activity on the Moon, around Mars, or eventually in the asteroid belt are not yet fully settled. That means the nations building capability now are not only preparing to explore, they are preparing to influence the legal and political grammar of exploration itself. And yet, there is still room for another possibility. The more crowded space becomes, the harder it may be to sustain purely adversarial models forever. Celestial mechanics does not care about flags. Scientific problems often exceed the reach of one nation's instruments alone. Infrastructure in orbit and beyond may eventually require interoperability simply because total duplication becomes too costly or too dangerous. A future solar system divided into rigid rival camps is conceivable, but it is not inevitable. Competition may remain intense, while practical cooperation slowly expands in selected areas, especially as more nations beyond the two great powers insist on participating in ways that complicate simple bloc politics. What China has done, above all, is make that future impossible to ignore. It has ensured that any serious discussion of the next century in space must include Beijing alongside Washington, and likely alongside a growing number of others. The map of the future solar system will not be written by one power, or perhaps even by two. It will be written by a shifting network of states, agencies, companies, and scientific communities, all trying to decide where they belong beyond Earth. And if that sounds abstract, the Moon offers a way to make it concrete. Because the future political map of space will ultimately rest on something very practical. Where can you land safely? Where can you find water? Where can you shelter from radiation? Where can a base actually stand? Before any nation can turn ambition into permanence, someone has to map the ground well enough that another world stops being only a destination and starts becoming a place. That practical transformation of another world into a place begins, almost always, with mapping. Before there can be outposts, extraction sites, shelters, landing corridors, traverses, or long-term scientific stations, there must first be a patient act of seeing. Not dramatic seeing, not symbolic seeing, but systematic seeing. The kind that turns a distant body from a shining circle in the sky into a landscape of slopes, shadows, temperatures, materials, hazards, and possibilities. In the case of the Moon, much of that work has fallen to orbiters, and in the long arc of lunar exploration, few have been more influential than the Lunar Reconnaissance Orbiter. Launched in 2009, the spacecraft began with a straightforward premise: survey the Moon in unprecedented detail, map its surface, build the kind of dataset future missions would need if humanity ever intended not merely to revisit the Moon, but to remain there. That wording matters, because mapping can sound passive when it is anything but. To map a world is to prepare it for action. It is to convert curiosity into infrastructure. Every crater measured, every thermal anomaly logged, every slope resolved into meters rather than guesswork. Each of these becomes a future decision waiting to happen. At first, the orbiter's task might have seemed almost administrative compared with the romance of landings and rovers, but over time its importance became clearer. The Moon turned out to be more varied, more useful, and in some ways more surprising than a simple grey ball of dust and rock. High-resolution imaging revealed scarps, boulder fields, impact patterns, layered geology, and countless subtle details of terrain. Thermal measurements opened a new view of lunar extremes. Other instruments traced radiation, topography, and the faint signatures of volatiles. Little by little, the Moon ceased to be just familiar and became legible in a deeper way. One of the most intriguing findings is also one of the simplest to describe: a hole in the ground. Not a poetic metaphor, not a grand volcanic mountain, not a glittering ice plain, just a pit. Yet a pit on the Moon can be an extraordinary thing. Certain pit craters appear to be collapse features rather than impact craters, likely formed where underground voids gave way beneath the surface. That raises the possibility of lava tubes or cavern systems below, relics of an earlier era when molten rock moved beneath a crust that later solidified and emptied. The significance of such places is difficult to overstate. First, they are geologically valuable. Subsurface voids could preserve a record of lunar history better than exposed surface regions, continually battered by micrometeorites and radiation. Second, they are physically useful. The Moon has no substantial atmosphere and no global magnetic field. Its surface is exposed to radiation from space and to severe temperature swings between day and night. Building habitats directly on the surface would require immense shielding, but a natural cavity beneath tens or hundreds of meters of rock provides that shielding almost automatically. A lava tube on the Moon is not just a geological curiosity, it is a ready-made shelter waiting for a species clever enough to use it. This is a perfect example of how the modern space race is changing. In the first era, reaching the Moon at all was the great feat. In the second, the questions become more specific. Not can we get there, but where exactly should we go? Which terrain offers protection? Which offers access to valuable materials? Which offers science-rich exposure of the crust or mantle? Which gives us sunlight when we need it and darkness when we can tolerate it? The Lunar Reconnaissance Orbiter has helped make those questions answerable. Water is perhaps the most practical of them all. For a long time, the Moon was imagined as almost perfectly dry. If any water existed, it was expected to hide in tiny amounts, perhaps only in the coldest, permanently shadowed regions near the poles. But the reality turned out to be more subtle. Instruments detected trace amounts of water-related chemistry in the surface regolith across broader areas than once expected, and evidence accumulated that the Moon participates in a faint, shifting water cycle of its own. The quantities are small, but their existence changes the strategic imagination of lunar settlement. If water or hydroxyl is more widely distributed than once believed, even in minimal amounts, then the moon is not just a sterile outpost waiting to be supplied forever from Earth. It becomes a place with gradients of utility. Then there are the permanently shadowed craters near the poles. These regions never receive direct sunlight because of the moon's slight axial tilt and the geometry of crater walls. They are among the coldest places in the solar system. Temperatures there can plunge lower than those on Pluto. Such cold is more than an environmental curiosity. It turns those regions into natural traps for volatile substances, especially water ice delivered or preserved over immense spans of time. If usable deposits exist there, they could become the foundation of a true lunar economy. Water is not just drinking water. It can be split into hydrogen and oxygen for fuel. It supports life support systems. It underwrites permanence. But the polar regions are difficult. That is the catch. The very places most likely to contain trapped volatiles are also places of brutal cold, deep darkness, and treacherous terrain. Shadows conceal detail. Rims create sharp contrasts. Navigation becomes harder. Energy supply becomes less straightforward. Once again, mapping becomes the precondition for action. You cannot establish a base, land repeatedly, or extract resources from a region you do not understand in intimate detail. This is where South Korea's Danuri mission enters the story in a beautifully complementary way. Danuri, the nation's first lunar orbiter, carried among its instruments a NASA camera called ShadowCam, an extraordinarily sensitive imager designed specifically to look into the darkness of permanently shadowed regions. It is a wonderful symbol of the age we are living in. A South Korean mission carrying an American instrument to reveal hidden terrain on the moon for a future that will likely involve many other nations as well. The hardware itself becomes a statement about the character of modern exploration. ShadowCam works by doing something obvious in concept and difficult in practice. It makes darkness usable. Regions that previous cameras could barely register become visible enough to study. Crater interiors, slopes, boulder tracks, and subtle surface features can emerge from blackness. That does not mean all mysteries vanish. Some regions still guard their secrets. But the moon's hidden geography starts to open in a way that was not previously possible. This matters for more than safety. Once you can see into the shadowed regions, you can begin to connect the moon's practical future with its scientific one. The same crater that may shelter ice may also preserve records of ancient bombardment, volatile transport, or the long interaction between sunlight and darkness at the limits of temperature. Resource and science need not be rivals there. On the moon, as so often in exploration, the place most useful to settle may also be one of the most revealing to study. The moon, therefore, stands at a fascinating threshold. It is no longer merely the object of nostalgic return. It is becoming the first serious testing ground for long-term extraterrestrial presence. That shift changes everything. Questions that once belonged mostly to science fiction now become engineering questions. Where should habitats sit? How do you manage thermal extremes? Which regions offer near-constant light for solar power? Which terrain gives fast access to ice while remaining navigable? Can lava tubes be entered safely? How much local material can be used for construction? What kind of communications network will link polar outposts, orbiters, and Earth? Once those questions take over, the entire history we have traced begins to converge. India's Mars mission showed that new nations could look at familiar planets with fresh perspective. The United Arab Emirates treated Mars as a climate system and showed that even a young space program could contribute meaningfully to planetary science. Japan demonstrated that precision landing can redefine what is reachable on the moon. Britain and Zambia revealed how national identity, pride, and historical memory shape the meanings of spaceflight, even when programs stall, vanish, or remain half symbolic. The Jupiter Icy Moons Explorer showed that modern exploration is increasingly multinational in its very structure. Venus reminded us that worlds often require many wavelengths, many missions, and many generations of inquiry before they yield a proper picture. China's rise made clear that the political future of space will be multipolar, contested, and impossible to understand through the old Cold War script alone. Now the moon brings all of that down to ground level. literally, because the future of space will not be decided only by speeches, budgets, or launch tallies. It will be decided by whether we can transform knowledge into sustained presence. Mapping into landing, landing into shelter, shelter into systems, systems into habitability. The moon is where those translations are likely to happen first. And that is why the old phrase, space race, has to be handled more carefully now. It still has some truth in it. Nations do compete. They still care who lands first, who returns samples, who builds stations, who sets standards, who controls infrastructure, who inspires the world. But race is no longer the only word that fits. What we are watching now is also a diffusion, a spreading outward of capability, ambition, and authorship. The heavens are no longer narrated by just two capitals. More flags are rising, yes, but so are more instruments, more viewpoints, more alliances, more forms of participation. In a deeper sense, this makes the new era more human than the old one. The first great age of spaceflight was spectacular, but narrow in voice. The new age is messier, slower in some ways, less cleanly triumphant, yet far richer in what it reveals about civilization. It tells us that the urge to explore was never confined to the richest or loudest powers. It lived in emerging nations, in forgotten programs, in bold planners, in scientists working across borders, in engineers building unglamorous systems, in orbiters patiently tracing terrain year after year. The wider story was always there. We are only now getting better at seeing it. And perhaps that is the final lesson hidden inside all of this. Space exploration does not simply show us other worlds. It shows us what kind of species we are when confronted with distance. We are competitive, certainly, proud, territorial, anxious, strategic, but we are also collaborative, persistent, curious, and strangely unwilling to let mystery remain untouched. We build cameras to see into shadow. We build landers to touch points no one could once target. We build spacecraft that carry the labour of many nations inside them. We keep returning to difficult planets and difficult questions. Even our failures leave artifacts that reshape what later generations think is possible. 100 years from now, the history of space may not read as a sequence of isolated national triumphs at all. It may read as the long, uneven process by which humanity slowly learned to distribute itself beyond Earth, first in imagination, then in machines, then in infrastructure, and finally perhaps in durable communities. If that future comes, its roots will lie in exactly the kinds of missions we have been tracing here. Orbital surveys, modest national breakthroughs, precise landings, collaborative probes, rival architectures, hidden water, mapped caves, instruments staring into darkness until darkness becomes terrain. And when that future generation looks back, it may find the old superpower story surprisingly incomplete. Not wrong, but incomplete. Because the real modern history of exploration was never only about who reached space first. It was about who kept widening the doorway after the first footsteps were made, who insisted on joining the story, who found new ways to see, who built the tools, who returned to the hard worlds, who prepared the ground. That is the story now unfolding above us. Not a duel, but a multiplication. Not a single line of progress, but a growing web of ambition stretching from Earth toward the Moon, Mars, Venus, Jupiter, and beyond. A web made of science, pride, memory, rivalry, cooperation, caution, and extraordinary patience. A web that tells us the most important fact of all. The future of space will belong not to one nation, and perhaps not even to a handful, but to every society determined enough to look up at the night sky and decide that it, too, intends to remain part of the journey.